Lydia, you can record. Can, oh, hold on. Hang on for 1 second. Okay, can you all hear me?
Yes.
Okay. I've given you the ability to record, and as a matter of fact, how many we got here? 14. What I'm going to do is this. I'm going to make you, Lydia, your co-host, so you can admit anybody now too that tries to get in. That way I can focus on this. Okay, I'm going to get 18.
How do I do that?
You'll see when somebody comes in next that tries to get in, they'll be in a waiting group that you should be able to view. Give me a second.
Okay.
Next time somebody's trying to get in, I'll see if you can see them. All right. See, can you see Ruth Adams?
Yes. Okay.
Admit her. There you go. And that way it'll take me out of that loop. All right. How many we got? 18, right? We had 19 a second ago. All right. Well, I mean, everybody's getting this link. Did everybody? I sent back the test to everybody. I did my best scoring it. I spent more time trying to get things in a format that I could write on and score and get it back to you. And I've learned a lesson. I think Brandon's up there. Yeah, good. So everybody got their exam back to them via email. If you didn't, let me know. Send me an email. But you should have gotten your exam back. And if you have specific questions, you can talk to me right after this, this class today. So what we're going to do today, I'll just tell you, is we're going to go through Z transforms. Now, what I want to do is kind of show you why a Z transform is so important. And also want to make mention of something about difference equations, because I want you to see the importance and the similarities between how differential equations are really analyzed and viewed by either Fourier or Laplace transforms. Difference equations, those are something we can computationally do very easily, are analyzed and or created using either DT, FT, DFT, or Z transforms. So try to understand my motive for what I'm about to do. And now I'm going to cast the screen, assuming it works. This dot camera. Hold on for a second. I got to get the dot camera working. Come on. This has been happening routinely to me, and I don't know why. Let me try it again. Sorry, it was working. That was. Okay, I got it now.
Hey, Dr. Baginski,
Yes,
do you know when our final is for
I
this
don't.
class?
I don't. Not yet, anyway. I
Okay.
will. I'm sure somebody can look it up.
I tried to find it on the Auburn website and I didn't see it.
I can tell you. Can y'all see this? It should be my arm. You see it?
Yeah.
Yeah, we can.
All right. All right. What I'm going to do is go through the Z transform analysis and just tell you, just mention a thing about difference equations and try to bring everybody into getting an understanding of where I'm going with this and my motives. So I'm trying to, let me zoom this out a little. I wish I could get, this is about as good as it gets. All right. So with that in mind, let me go ahead. Focus, there we go. Typically, if we have a differential equation, we have something like this, dy dt plus ay equals x. These are all functions of t, both x and y, correct?
Mhm.
Okay. Now, if you take a look at this and you replace this with a difference equation, dy dt really is y of t plus delta t minus y of t over delta t, or in terms of a difference equation, it would be y of n minus y of n minus 1 over delta t, in this case ts. TS is simply the sampling interval, or it's the time between samples. And when you think about dt, really dy dt is y of t minus y of t minus delta t over delta t. That's one method. You could use a central difference theorem, but for now, I think you all see the analogy. Then it's plus a times y of n equal x of n. Does everybody see the relationship between the differential and the difference equation? This is a first order. It's about as simple as it gets. Do y'all understand that, guys? Just give me a thumbs up or something. Let me try to get the screen so I can view it. And this is a bit, okay, I got a few thumbs up. I assume everybody sees it. If you have a question, please ask it. And let me tell you one other thing. Sometime later today or tomorrow, I'll give you the curve on the test, all right? Right now I can't for a couple of reasons, but just bear with me and we'll get that information out to you. Now, when I take a look at this, I want a strict difference equation, so I multiply by TS, everything. And I assume everybody can follow me on that, right? I multiply by TS. And if you'd like to turn on your screen so I can see you, it helps me immensely to figure out whether I'm getting through or not. I mean, if you don't want to, you don't have to, but I'm just asking as a favor to me. It helps the interaction. And if the bandwidth gets if it becomes a problem where we're getting phrases and stuff, then I'll ask you to turn them off. Are you with me on this much so far? Okay. Now, what we normally do is solve for y of n. That would be the system output. So you take everything to the other side and you have y of n equal to, and then it would have x of n times ts, right? That checks that box. Then it's going to be, and I should have done this. I should have gathered 1 plus ATS right here. That accounts for this term and this term. Do you all see that, class? I'm simply taking y of n, it's multiplied by 1 here, and then y of n, it's multiplied by ATS here, and putting it here. Then I have y of n. On the other side, I have TS x of n, and then it's going to be plus right here, y of n minus 1. I think everybody sees this. It's fairly obvious if you just take one look. Y'all see it? Thumbs up. I see some head shakes, but most of the people I can't see. Okay. And again, if you could turn on your screen, it helps me a lot. I've learned the lesson the hard way. Now, if we have this, we would then divide by 1 plus ATS. And this is called a difference equation. And what you're doing is solving for the y of n using x of n, that's the present value of x, and the past value of y, n minus 1. Now, this is very easy to implement. And in general, with difference equations, what they're really doing is forecasting the current value of y of n based on the past history of either x and, or really it's the past history of x and y, or current value. That's a difference equation in a nutshell. And then you can create a difference equation from any differential equation, knowing that the derivative dy of t is simply equal to y of n minus y of n minus 1 over ts, delta t. And that means a second order if you take a derivative of this, the only thing would be is then you would have y of n minus 2 times y of n minus 1 plus y of n minus 2 over ts, 2ts. But I don't want to mess with that right now. I just want to make sure you understand the relationship between a difference equation and a differential equation, okay? The two are exactly equated for a sampled signal. They become identical. That's the only thing. Now, the next thing I'm going to do is talk about the relationships of these things to the transforms. We know if we had the simple differential equation dy dt plus ay equal x, this is time domain. If we looked at this, we could take a Laplace transform of both sides, and it'd be useful. We could actually get the frequency response from the Laplace transform, just taking the Laplace transform of this, assuming no initial conditions. Then we get sy of s here, right? Plus ay of s is equal to x of s. Does everybody agree with me there? If it seems fundamental and too easy, trust me, it's going to get a little crazy in a second. But I got to bring you up to speed. Now, that is an obvious relationship between differential and Laplace. Now, I can see that y of s over x of s here would be equal to simply 1 over s plus a, and that would be h of s. That's the system transfer function, relates output to input in the s domain. If I wanted the continuous, wanted the continuous time frequency response, I would put h of omega, and I would let s become j omega, and I would get this. I would simply get 1 over a plus j omega. Does everybody agree with that? I just replaced s by j omega. Y'all, I mean, it seems very obvious to me, but I got to make sure. Okay. And if you don't, just let me know, and I'll try to make it clear. So this is a frequency domain response, and we could get magnitude and phase from here, couldn't we? The magnitude would be what?
1 over the square root of a squared plus omega squared.
Right. And what would the phase of h of omega be?
Inverse tan of
what you want to say is here would
over
be tan minus 1, inverse tan of omega over a downstairs, right?
yeah.
All right. And then when it comes upstairs, it's minus the tangent of minus 1 of omega over a, correct? Just take 1 over tangent is minus tan, correct? This is really an angle, isn't it? I don't know who's looking. I don't know who is talking, but y'all see it's an angle? Well, if you take 1 over the angle, it becomes minus that angle. So this is really the angle there, correct, class? It would be in radians. Okay? Guys, all right. I'm working here. I'm really trying to get through.
Could you
But
explain the phase again?
yeah,
I get
let me just
magnitude.
ask you this. If I have 1 plus j omega, I mean a plus j omega, that means I have a here and j omega here, right?
Yes.
All right. When I look at that, that's the angle, isn't it?
Oh, okay. All
And
right.
the angle would be opposite, which would be omega divided by a. The opposite over the adjacent would be the tangent of that angle, and therefore the angle is tan minus 1 of that would be theta. That's my point. But I want to make sure I answer questions, because here's where people get lost. They don't understand how to get the angle. They don't understand something fundamental, and it becomes crucial.
Oh,
Got me?
Dr. Baginski, I don't quite understand how you got the negative sign on the tan.
All right, let me ask you this. If I have 1 over 1 at an angle of 90 degrees, what is that really?
Okay, that's one negative 90 degrees.
That's it.
Gotcha. Okay, thank you.
That's where that negative sign comes. Remember, it's an angle, not a magnitude. It's an angle. Okay? In radians. Unless you specifically say degrees, it's in radians. All right. Now, we know how to analyze both in, we can design with Laplace, right? Laplace was our tools where we could construct H of S. If we had an H of S, we could build it with parts, with resistors, capacitors, and op amps, right?
Mhm.
All right, and that was a very powerful thing. You could create a circuit to realize your transfer function, either a filter, low pass, high pass, band pass, whatever you wanted. It could be anything, and that's important. Now, the next phase we went from, and I'm not gonna do the discrete, remember we did Fourier series analysis for periodic functions. There is a discrete time Fourier series is when the periodic function is sampled. I'll do that at the end of the course if I have time, but that's not that critical right now. All right. Remember, what I'm trying to do is hit the high points in this stuff. There's so much material we could cover. I'll get to that later. But now, after that, then we looked at sampled signals, didn't we? And when we did sampling, we found out that then x sampled of t was equal to x of t times an infinite series from n equals minus infinity to infinity of delta t minus nts. And ts is the sampling interval.
Can you move the
Could you-
paper down a little?
Yes, thank you. I'm going to try to remember to look up there. There you go. And please yell at me if it isn't apparent. Y'all with me on that? That's just sampling a signal, right? This is a continuous time signal. I'm sampling it and getting points in continuous time at NTS, every NTS. Correct, class?
Mhm.
Now, when we did that, there was something that happened. I won't go through the entire translation, but then the Fourier transform became what? It became x of omega. It became the dtft, correct?
Mhm.
And when we did that, we found the dtft was actually equal to what? Not an integral, but a sum from n equals minus infinity to infinity of, now it's x of n, right? We suppress the ts, and it's e to the minus j n omega. And that capital omega is really the small omega times ts.
Okay.
All right, I'm trying to bring you up to speed. Now, this is something that you can actually take a differential equation, and you can take the dtft of it and get a function. You can get y of omega over x of omega as the transfer function, and it would be in a capital omega domain. Now, do you all remember doing that a little bit, right? All right, we did that. One of the problems with this is, even though we're getting closer to something that can be applied to something in real time with a finite memory, the real problem with this is the summation goes from minus to plus infinity, which is you can't do. So the next step was to go to what? The DFT or the FFT. And when we did that, and there are inverse operations to everything I'm showing you. I'm not doing them right now. But this brings down to what? Then you get an x of k, and that was equal to a summation of x of n times e to the minus j, and it's 2 pi over n, where n's the total number of points, n times k here, and here, this is going to be n goes from 0 to n minus 1. And that's the DTFT. Do y'all remember that?
Mhm.
This is the progression. We went from continuous time using Laplace and Fourier for either analysis or synthesis. Now we're going to the sampled waveform, and now we're going to something that is realizable. And here, the thing that was the point I wanted to make is when we wanted to look and think in terms of something that we know fairly well, the Fourier transform, we could get a direct comparison where the x of Fourier, omega here, would be 2 pi over n, right, ts times k, and that would be equal to 1 minus e to the minus j, and this would be 2 pi over n times k, the ts would go away in the numerator, divided by j times 2 pi over n ts k. If you don't remember this, trust me, it's in your notes, times x of k, and this x of k is just the FFT. And you did a comparison and you showed, you proved to me, you proved to yourself, that in fact, if we did this and adjusted the DTFT, we get something that compares exactly to the Fourier transform, assuming we sample it fast enough so the values of x of n and x of n plus 1 are about the same. Y'all remember that?
That was that MATLAB assignment.
Yeah, you had several problems that you did. And that was the whole point, to see this for yourself, to prove it to yourself. Make it something that's not abstract, it's something real. You've actually done it and seen it. All right, now today what we're going to do, because we understand analysis, this FFT and this, the DTFT is really the sample time analysis of signals. Now we're going to do something with Z transforms, and we're going to introduce Z transforms by starting with the Laplace transform. And please appreciate the significance of this. The real benefit of Laplace was you could do design, right? Synthesizing things. That was the strength of Laplace. All right. So and you can also analyze more signals with Laplace. So now we start with the actual Laplace transform, x of s of a signal, x of t. And that's equal to, in our book, in most work in engineering, you always do what's called the single-sided Laplace transform, which starts at 0, not minus infinity. It goes to infinity of x of t e to the minus st here times dt. That's a 0, not a q. That's Laplace, right? Here's the next. Anybody want to take a guess at what my next step is? Remember, we're in discrete time. Anybody?
This is not the answer, but could you zoom in a little bit on the page? It's kind of fuzzy on my end.
Yeah, it's fuzzy on my end. There you go.
Thank you.
This has an autofocus, but sometimes it needs a reminder. It does have an autofocus.
This might be the wrong answer, but do you want to turn t into n times ts?
Almost right. What you want to do is that's exactly what's going to happen, but really what we do is we say that now we're going to have x sampled of t equal to x of t times the summation of delta of n, or delta of t, pardon me, t minus nts, where n now goes just from 0 to infinity. My real point is we're sampling x at the points nts, but you're right. In fact, we're evaluating this at n times ts points. That's exactly right. Now, when we do this and we put this in here, you don't have to write this down, but the first time you do it, you get x of s here equal to an integral from 0 to infinity. And here's my statement of purpose right here. You all agree that this thing turns on at nts, right? All other values, it's 0. So x of t really only has a value at x of nts. So I'm going to write it down like that. Now I have the summation from n goes from 0 to infinity of the delta function of t minus nts. And it's times e to the minus st dt. This is very similar to what we've been doing. Do y'all agree with me there?
Mm-hmm.
I've just restated the equation above here, but now I've put in the sampled signal for x of t, correct, class? Okay. Now you change the order of operations. You do the integration first. You'll notice this is not a function of t. You'll change the order, and when you do this, now I get a summation. I have x of s equal to a summation from n equals 0 to infinity of x of nts times an integration from 0 to infinity of delta of t minus nts times e to the minus st dt. This is almost identical to how we got the dtft, except we didn't have e to the minus st, we had e to the minus j omega t. You with me, everyone?
Mhm.
All right, and what does this become right here? When is the delta function on? For t equals?
NTS.
Right, so you
Yes.
put that right there and extract it. So now we have this. And we do one other thing. We suppress the TS. Generally, they put square blocks on things that are functions of n. I don't use that usually because it's harder for me to do that. Then you have e to the minus s times TS times n right there. And now we define the Z transform. We do this. We say the Z transform x of Z is equal to the summation of n equals 0 to infinity of x of n times times Z to the minus n, where Z is equal to e to the STS. And this is called the Z transform. I'll do the inverse Z in a second, but I want you to appreciate how we got it. We started with the definition of Laplace, then we assumed the signal sampled, and after that, we've created a new value, Z, which is equal to the e to the STS. I'm going to talk about this for a second, okay? I got to turn the page. So what is Z exactly? What does it look like? If you look at Z, is equal to e to the STS, right? That should be S.
Can you move it down?
Yeah. It's equal to, Z is equal to e to the ST sub S. Now, what is S? It's equal to some real part, sigma plus j omega, correct, class? It could be like 5 plus j20. It's a real and imaginary number. The sigma is something that causes damping of the signal. Now we look at Z, and that's equal to e to the sigma plus j omega times TS, right? Or it's e to the sigma TS, right there, times e to the j omega TS. Remember, e to the j omega TS is really capital omega. And here, Z is really equal to some rho, where rho is a radial distance. All right. And then, rho times e to the j capital omega. Let me rewrite that. Z is equal to rho times e to the j capital omega. Now that omega here is the same omega as the dtft. It's periodic in 2 pi. From minus pi to pi, looks exactly the same as from pi to 3 pi. It step and repeats. But this is what the Z variable looks like. And rho is a radial distance. Rho is actually equal to this. That is rho. Now, there are a lot of things that you're uncomfortable with or have questions about that you probably can't even form well. There's a lot of things you see, but there's things you don't see, and you don't even know how to ask it yet. You want to see probably why we're doing it. This is going to come together in a second. Just think back for a moment. When we did Fourier transforms and Laplace transforms, how many things you were uncertain about, but hopefully the questions were answered when you saw the actual fabrication of circuits, right? A lot of that comes together in time, but right now, accept this definition. Now, some things about the Z transform. Again, it's the Z transform and the DTFT are identical if you have values of x of n that are only non-zero for n equals 0 or greater than 0. In other words, it's just like the Laplace and the Fourier transform. If you had any x of t that was only had values of interest for t greater than 0, then if you had the Laplace transform of that, you could get the Fourier by just letting s be equal to j omega. Does everybody recall that? Here, it's the same thing. You can say x of capital omega is simply x of z, where z is equal to e to the j omega, if and only if x of n has values that are non-zero. It should say x of n only valid for n greater than or equal to 0, and x of n equals 0 else. So here, if you have x of z, you can get x of omega by simply putting z equal to e to the j omega. That is the exact analogy to a Laplace transform being used to get a Fourier by replacing s with j omega. Okay, next. So big deal. I'll show you some things about these things that have become interesting. X of z, therefore, for any finite or any series that is only valid for n equal to or greater than 0 is equal to the summation of n equals 0 to infinity of x of n times z to the minus n. And z has a rho times e to the j omega. Now we're going to talk about some of the properties of the Z transform that are important. Well, we're going to do a few Z transforms. Then we're going to talk about some of the things that Z transforms do for us. Let's do a few Z transforms. I've got notes here. I'm more or less doing exactly what my notes say, but I always take the liberty to, if I have to answer questions and go off on a tangent for a second to try to straighten everybody out on something they might not understand, I'll do that. For this one, let's just do a few. Suppose this is x of n on this side and this is x of z. Now remember, in all the prior times when we had Laplace, Fourier, right? We always did what? We found only a short number of transform pairs by using the actual definition of the integrations or summation. That was true for the DTFT. And then we used what? Properties to get all the other ones, right? All right, that's how we always do it. Well, we'll use the fundamental definition here to get these. So if I have delta of n, probably the easiest thing to see is a delta of n function. What is delta of n? It's 0 everywhere except what, class?
0.
0.
When n is 0, what is its value?
1.
Not infinity, 1, right? So plug this into this thing. All right, n equals 0. I have 1 times z to the 0. What is z to the 0?
1.
So I have 1. Then when n is 1, I have 0, n is 2, 0, and so forth. So this is 1. That's one of the things that seems to hold true everywhere you see it. It's true in Laplace, it's true in Fourier, it's true in DTFT, and it's true in Z. That transform is something that exists in continuous and differential time, or I should say in discrete time. All right, next I do this. What is delta of n minus, say, call it k, where k is an integer. Just look at the definition. Where does this turn on?
A.
Okay.
N equal k, right?
Mm-hmm.
So when n is equal to k here, you would have z to the minus
A.
Okay, right. That's it. You probably in your head, it's the similarities between that and the Laplace and the Fourier and the DTFT are, you're seeing it now. Very similar, right? Next one after that. What do we get for, and I want to tell you, if you're looking for where these are, and it's fine to do this, you can look in your book, it's on 368. Page 368 in your book. All right, now do it yourself, just don't look at it. What about U of n? Do this one just longhanded. If I have U of n, what does this series become? What does x of z become right here? Now let me work at the bottom of the page here. X of z if x of n is equal to U of n. That's equal to what? The summation of n equals 0 to infinity of
1.
1. That's right. Times z to the minus n, right?
Mhm.
All right.
So is
Well,
it just 1 over z?
yeah, well, that's exactly right. But let's do it. You're right. Of 1 over z, right? So isn't that, I mean, that's 1 over z to the, this to the n power, right? Z to the minus 1 is 1 over z to the n.
Yeah.
Agree? Everybody see that?
Mhm.
All right. Well, what is that going to be? Isn't that like a to the n?
Yeah.
Yeah. Well, what does a to the n go to? It goes to a to the this, which is 1, right? Minus a or minus 1 over z to the infinity plus 1, which is still infinity, over 1 minus z, right? Or I mean, 1 over z, correct?
Yes.
Now, this will go away because we're going to be talking about a region of convergence that will remove that. We'll tell you what will happen is this will always have to go to 0 for convergence of the series. And so we're left with 1 over 1 minus z to the minus 1. Let me flip the page on this. Or U of n or U of n here would go to, I have 1 over 1 minus z to the minus 1, right? Or in the book, it'll have it z over z minus 1. Either form is correct. Y'all see it?
Mhm.
Now, think back. What was U of n when we had the DTFT? Wasn't that 1 over 1 minus e to the minus j omega? And then there was a stipulation that this thing's got to repeat itself every 2 pi. Do you remember that? You would have to add that stuff over here that would repeat this every time you add 2 pi to the argument of omega.
Yeah.
All right. Well, you don't need to worry about that with z transforms. All right. So that's nice. It's not there. But this is the transform pair. I mean, this is the relation to DTFT, but it has this stuff here. So for the z, it's that one. And if you look in, I think that's the third one down, or second one, right? It's the third one, but they have 1 and 1a and then 2 on page 368. Y'all see that?
Mhm.
All right, next one I'm going to do, and I bet you all get this. Fundamental definition of x of z is the summation of x of n times z to the minus n from n equals 0 to infinity. That's the definition.
Mhm.
Now, what if I have a to the n u of n equal to x of n? Well, if I have that, and I stick it in that series, I have x of z equal to a summation. These are the base ones we have to have. X of z from n equals 0 to infinity of a to the n u of n times z to the minus n, or really it's a over z to the n. And the u of n you can forget about because it's only valid for n greater than or equal to 0, right?
Mhm.
Does everybody agree with me there, people?
Yep.
Yeah. I mean, give me some evidence that you're there and viewing and not watching TV or an old Alabama Auburn game. Okay. Speak of that. You realize how the sports networks are just running out of money? They don't know what to do. They're replaying all the old Federer against Rafa Nadal tennis stuff. Then they got another ESPN, all the football games that are like localized to the Southeast, the Iron Bowls from ages gone by.
There was this huge party in Dubai where they were betting over like some amateur bowling.
Bowling. I'll tell you one thing that is popular, and I'm more popular than ever. I live right on a golf course, and there are more golfers going by, and everybody's got their own cart, just one person per cart, but it's nonstop. It's just the groups of 4 coming through here, left, right, left, right, left, right, continues. So if I had stock in that, I would buy a ton of stock in these golf courses right here if I could, because they're not slowing down. Neither is all the traffic on Lake Martin's boating, from what I understand. Anybody have been out to Lake Martin or any of the lakes? All right, well, it's crowded that has not gone down.
Too rich
Yeah,
for my blood.
Yeah, I live on a lake back home, and so it's still cold, but I mean, the amount of people out for the time of year it is here is ridiculous.
They're actually wearing partial wetsuits. I see jet skis flying by, but mainly fishermen where I go. And I mean, it's now that everybody's they got to find something to do. Well, yeah, if it ain't golf, it's probably fishing or hunting or something like that. All right, so this is, what does this series go to? Now what happens?
Is that A over
Z?
Z over Z minus A?
Yeah, you know exactly what the right answer is. Here, this A over Z looks like our A, right? It looks like the A from before. And that means you get what? 1 over 1 minus A over Z, correct? And then that means it becomes simply Z over Z minus A. Now that's the exponential decay, I think of it that way. And that's number 4. And now I got to talk to you about the region of convergence. So here, now, hang on. I got somebody coming home. Jen? I didn't know what was going on. Anyway, now I'm going to put on a different screen. I'm going to stop the sharing, okay? I'm going to show you the Z transform. I'm going to go to a PowerPoint just to show you one thing. I'll come back to this stuff right here. Where is my share screen stuff? Stop share. And then I got to start share. Where's that thing? All right, now I got to share a different screen. All right, what you should see is a PowerPoint. You should see a PowerPoint with Z transforms. Do y'all see it?
Mm-hmm.
Yes.
This is not going to last but for a second. Oh, come on. What do you do here? Put you over there. All right, let me take you through this. Don't worry about all that. Don't worry about that. I already did this. Notice one thing. Can you see my cursor on the screen, people?
We don't see the presentation. We only see the original PowerPoint window.
Okay. Let me do this then.
Also, just so you know, you have about 5 minutes left.
Thank you. I'm trying to do this. Let me do it this way. See if this works. Do you see a thing that says Z-plane?
Yes.
You do?
Yep, we do.
All right, and when come on. Yeah, perfect. All right. I want to mention something. This is the DTFT down here. My cursor's on it, and I hope you all can see it. You'll notice how the DTFT goes from minus infinity to plus infinity. You all see that? Now, there's two types of Z transforms, just like there's two types of Laplace. This is a double-sided that starts at minus infinity. This is rare. Almost all the things you do starts at 0, because we're engineers and we like to make, we can start everything at 0. And the values for like -1, x of -1, and x of -2 are only for the initial conditions. So that bottom term here will always be 0, right there. Now, this is what I wanted to get at. Don't worry about that. But when z is equal to e to the minus j, that should be a capital of omega, but a lot of books that do signals and systems use small omega. What you see is you're right at this radial distance of 1. Think about the definition of z. It's equal to rho e to the j omega, correct, class? Well, if you let rho be 1, then you have the DTFT of any signals that have values that are non-zero for n equal to or greater than 0. And you're running on this rim right there. And you notice omega goes from 0 to 2 pi, and then it's the same thing again. Do you all see that? All right, so it repeats itself, as it should. But here's where it becomes real important you pay attention. Don't worry about that or that or that. I mean, he's just showing you, normally when we look at the frequency domain plot with a function, we just look at the magnitude of it versus value of capital omega, right? And it's periodic in every 2 pi, correct, class? When we talk about Z transforms, just like when we talk about Laplace, we talk about poles and zeros. Now, here's the thing called the region of convergence. It's ROC. A Z transform exists only when the Z transform is less than infinity. When it actually goes to infinity, it's called a pole. And I think you're familiar with the definition of poles from Laplace, right? A pole is something that causes, the value of s that causes a pole makes the function x of s go to infinity. So when we think about this with Laplace transforms, we take a look at the pole zero constellations, and any poles in the right half plane meant the system was unstable. Do you recall that? All right, watch. Now, what we get is this. We're getting what's called a region of convergence. And it's an annular ring, typically with an inner radius and an outer radius. Now, usually, but not always, usually the inner radius is 0. But I'll get to that. And that's called the region of convergence. I'm trying to get down to the fact Fourier transform is this is the DTFT. When he says Fourier transform, it's DTFT evaluated at z equals 1 circle. And a stable system, this is what I'm getting at. A stable system requires the region of convergence to include the unit circle. You see this is 1 here?
Mm-hmm.
It has to include that or it's not stable. By that, it means that the Z transform goes to infinity. And it also means one other thing. It means the system response in the h of n, the impulse response, will also go to infinity. It'll be non-stable. But remember this, for a stable system, it requires the region of convergence to contain the one circle, radius of 1. And I'll really bring this out in some examples. All right, now this is the one I just did. I don't need to go through this. It's a decaying exponential, and you all see that, right?
Yes.
All right. And the Z transform of it is what we just did. I don't even want to play this game. We just did that. Now, that's a right-sided sequence. It means its values are for x of n that are non-zero, for 0 greater than 1 or greater than 0. There's also, in the region of convergence here, if we have z over z minus a, is, just take a look at this for a second. What values of z in the original series would make that convergent? Remember, we had a to the n u of n right here, right? Well, what values of a make this finite summable series, where it will not the latter values will not tend to get larger than.
It has to be less than 1.
That's right. And it's pretty obvious if you look at it, right? So the region of convergence of this will be for z greater than or equal to a, whatever a is. And the one circle may be out here somewhere, you know. Can you all see that?
Could you
It'll
say
be-
that again? Sorry.
Yeah. If I take a look at just this series, right? The z transform for that series is this, right?
Yes.
All right, now look at this for a second. What values of a make this thing a finite summable series that will be the sum of this, forget z for a second, the sum of this thing will not be infinite. A less than 1, magnitude of a. Do you agree with me?
Okay.
That should make sense. If I add 1/2 to the n, well, that keeps getting smaller and smaller. 1/2, 1/4, follow me?
Yeah.
If I had 2 there, it would be 2, 4, 6, 8. It's growing. It's getting larger and larger, right? What that translates in, and Ruth, I know you got to go in a second. Just let me finish my point. That translates to the value of z has to be greater than or equal to a. Now, it has to include the unit circle, so a can't be greater than 1. And here's what the point is right here. See how a is there? Let me get 1. If a was greater than 1, then it would be unstable. Remember I said the unit circle has to be included in the region of convergence. Do y'all remember that?
Mm-hmm.
Yeah.
That means a has to be inside here for that thing to be stable. And this is stable here. This is unstable here. Did I make my point?
Mm-hmm.
Stable on the right, unstable on the left.
That's right. I mean, that's correct. All right. Thumbs up if you see this and understand. I'm going to let you go in 1 more minute at most. Oh, don't worry about that. All right. Don't worry about left-hand series. These things are useful sometimes in modeling, but don't worry about it. John Hung will cover that in his class in controls, I think. Dr. Hung. Come on. I'm trying to get to one other thing. All right. Now, I'm going to stop sharing this. And I got, what is this? Questions? Chat, I'm sorry. Wednesday, April 29th. What is this?
That's when the final is.
Oh, thank you. Thank you.
Yeah, I just posted up the day for the final.
I appreciate that. Send me an email with that. I want to be aware of it.
And it's got the link to the website at Auburn, so it has the list of all the classes for the entire semester.
All right. So let me just tell you this. I didn't get to the point I wanted to today, but I think you can see the case I'm building for the similarities between all these transforms and the actual discrete transforms. What we're going to do with Z transforms is go ahead and go through Z transforms and inverse Z, and then use the Z transforms to build actual circuits or block diagram circuits that will realize functions. And I'm going to go through low pass, high pass. I'll give you a reading assignment, some homework to do. I may ask that you deposit 1 in Canvas. I'm not sure yet. Okay. Any other questions? You guys can go. I'm sorry if I kept it too long. And I will, yeah, let me take care of that. And if you have questions about your test and stuff, then let's talk about it in the next day or two. And I'll try to do my best to answer them. And I'll get the curve information out to you, okay? All right, have a great day. I'll stay around if you got a question. I like that background. you got what is that? That's the Aurora Borealis, isn't it?
Mhm. Yes.
That's kind of cool. All right. Well, if there's no other questions,
I have one quick question. I
Go
know
ahead.
that since you were wrapping it up really quickly, I want to be sure that I have it. The region of convergence only works when you are within the unit circle.
No, when you include the unit circle, what you
Okay.
said is correct, but it could go from like A is a half to A is 1.5, as long as it includes the one circle.
Okay.
And when you get the region of convergence, once you get an inner and outer radius, that's when you have a double-sided series. For single-sided, it will
Okay.
always be at A or greater than A.
Okay. So you couldn't have a region of convergence that was only inside of the unit circle. You have
Only
to at some point cross it.
That would be a left-hand. That would be something that would have only be true for n negative.
Okay.
Don't worry about that right now.
Okay. All right. I think I understand that then. Thank you.
All right, guys.
Okay, and you said in the next couple of days you'll let us know about the curve and whatnot.
Yeah, I'm going to get all that out to you. I want to tell you, y'all you're posting this thing on YouTube, right? And there's no problem. Nobody's got any problems with this, seeing it?
Not so far.
Okay. All right. Well, go and I'll get you some problems to do and some reading. And then next time, what I'd like to do is go through applying the properties. They're very similar to what we did with the DTFT and Laplace. And you're going to see how much parallels and how obvious it is. But there's a couple things with Z transforms that are become super, super interesting, because you can literally, with your either microcontrollers or microprocessors, you can build filters, digital filters, very easily, and they're very effective, and we'll get into that. And they're things that, for instance, Jeffrey, aren't you a sound buff? You like doing things like, aren't you the one to talk about speakers and stuff? Or somebody else? I guess it's a different person.
I mean, I had speakers like way back in the day. It's been 15 years probably,
No,
but
it's somebody else who's talking to me, and you know what an equalizer is, right? You've seen that where you can, each individual frequency range you can change and stuff. Well, what you can do with, and this is interesting. Remember I told you a story about Professor Bose at MIT? And he had a passion for high fidelity sound when he just got out, but it was not available at a price range that was even reasonable to a professor at MIT. So he built his, and what he did was he took speakers that were just fairly inexpensive speakers, and he had a lot of them, and then he had a crossover network. And the network, what it did was provided that the amplification, or really the power coming out of the speaker for every single frequency was the same. So it had flat sound, and it was distortion free. That's a Bose 901. It had an active crossover. They found the actual transfer function of the filters. That's the frequency response in power in decibels per hertz. They took that and inverted that and realized that with a filter. That was an analog filter at that time. Now we do the same thing with digital filters, and the sound is basically free of any type of noise too. We'll get to that and you'll see. But see, audio guys, real audio buffs, they love this stuff because they can make a speaker system reflect what would be in an actual hall, a giant like Albert Hall. They can get all the background ambience and stuff like this. And they can basically have sound that sounds like you're in a forest in the background. And it's phenomenal what you can do. But that's more later on that one. Keep that in mind. I'll let you all go. Take care, everybody.
A quick
all
question.
righty.
Go ahead.
Will the homework be due on Friday, like always, or
Oh,
Monday?
how about Monday?
Okay, perfect. That'll be
That
great.
way on Friday I can answer questions.
Okay.
All right,
Okay.
but I want you to take a shot at it, so I'm not left redoing a lot of stuff. All right.
All righty.
Have a
Sounds good.
one. Take care. Bye-bye.
Yeah.
All right. Y'all too.
Bye.
Bye.
Bye.